Good. So I'm very happy I have a chance to discuss with you how NMR spectroscopy can contribute to this fast evolving, exciting field of intrinsically disordered proteins that were considered until recently just some kind of curiosity, some kind of outlier respect to the mainstream structure function paradigm that tells us that a protein function because of its three-dimensional structure. And indeed, looking into the early literature, Vladimir Uversky found out a bunch of different words used to define these kind of proteins, ranging from permutations of partially, natively, with intrinsically, with disorder and structure, all the way to more funny terms. And indeed, just by looking at the primary sequence of a protein, you don't need many predictors to figure out that this protein will never fold into a stable three-dimensional globular folds like the many that we find in the protein data bank. And therefore, in this context, we all know that NMR represents a really strategic tool for their investigation, as it can provide atomic resolution information about their structural and dynamic properties. And there are not many other techniques to achieve this job. I was impressed when reading the early bioinformatic papers, early work to really discriminate between order and disorder, and a lot of information was actually achieved from the residues for which information was missing in X-ray structures. So actually, indeed, we all know that in X-ray structures cannot capture this high extent of disorder and flexibility. And these properties also have an impact on NMR observables. So we should really do our best to optimize the experiments for intrinsically disordered proteins to use at best the power of this very sophisticated technique. And the first consequence deriving from the loss of a 3D structure is reduced contributions to chemical shifts. Indeed, conformational averaging averages out contributions deriving from the three-dimensional structure. And so the only contributions remaining are the ones deriving from the covalent structure. As one can tell by the first spectra we always acquire on a protein, a 2D proton nitrogen HSQC. And as you can see here, for two proteins of similar size, when passing from a structured protein to a disordered one, the chemical shift dispersion is greatly reduced, in particular in the proton dimension. There is something residual in the 15N dimension. So we should try to make a good use of this property. And now moving to our PET protein alpha-synuclein that we use to test all our experiments for IDPs. Here I have reported the chemical shift dispersion for 3 backbone nuclear spin, amide protons, carbonyls, and nitrogen. And they are actually shown in the same scale in Hertz. So one can appreciate the increase in their dispersion in the resonances. And this is actually nitrogens are actually one of the best contributors to chemical shift dispersion. One reason for which HSQC are still one of the best experiments to characterize IDPs. However, why don't we try to also correlate nitrogens with the attached carbonyl? And when looking at the 1D of carbon-13, if acquired on a uniformly isotopically labeled sample, the first thing that stumbles in our eyes are the large homonuclear scalar couplings. That, of course, will complicate our spectra and reduce the resolution. That is an important feature, in particular for IDPs. And so we should worry about this problem of homonuclear decoupling, which is a bit more demanding in respect to heteronuclear decoupling. And why? Just because we have to irradiate and decouple two nuclear spins that are much closer in frequency. And there are many solutions that have been proposed to solve this problem. For example, just alternating the time for acquisition between acquisition and decoupling, or for example, even using the convolution of the coupling itself, or more sophisticated variants of this approach. But in our hands, the method that we like more is based on spin state selection. In other words, the coupling is maintained, but two different components are acquired. For example, here I have reported the in-phase, anti-phase approach, and then by linear combination, the two components are separated. And finally, by shifting them to the center of the original multiplet, we do perform what we like to call virtual decoupling, in the sense that we got rid of the large scalar coupling without really applying any decoupling sequence. So how does it work in practice? Or actually, first I should mention that this approach can be appended to any experiment that is ending up with carbonyl magnetization. But in many of our experiments, the final transfer step consists in refocusing or some kind of antiphase of carbonyls. And so this approach can be simply embedded in the last block of the experiments without making it any longer. Here is the example of the CON, which essentially is very similar to proton nitrogen 2D with some little extra complications. And so in this final block, we can encode the two variants to collect the in-phase and anti-phase components of the signal, as I would like to show you here in a practical example. Indeed, this CON experiment acquired on alpha-synuclein without taking care of this aspect looks still quite crowded. But then we can collect actually the antiphase components, in which the two components have different sign, and perform our linear combinations to separate the two multiplet components, and finally achieve the desired effect. So this tells that we can get really nice 2D spectra, and these two experiments actually provide a nice fingerprint, initial fingerprint of our protein. And they actually correlate the nuclear spins involved in the peptide backbone, an important aspect that maximizes the covalent contributions to chemical shift dispersion, the main one operative in IDPs. And in particular, the CON experiments correlates to nuclear spins of different amino acids, contributing to its nice dispersion. It also reveals proline residues that lack the amide proton, and in alpha-synuclein they are just 5, but as I will show you in a minute, also through practical example, they result very abundant, as also proposed in the early bioinformatic papers. They were actually defined as disorder-promoting amino acids. Okay, so the other major effect that pops up in absence of a three-dimensional structure is the extensive exposure of these protein backbones to the solvent, so that amide protons get actually broadened by solvent exchange, in particular, if we try to approach a physiological pH and temperature, all the way up to broadening beyond detection. A practical example is shown here from this series of HSQC acquired on alpha-synuclei at a pH near neutral. And as we can see at low temperature, we can essentially monitor all the amino acids in the protein, but with increasing temperature, a number of cross peaks vanishes and the quality of the HSQC is greatly reduced. However, if we look at this, maybe there is some good, nice information because some peaks do remain. An important aspect that tells us that even if solvent exposed, they will not all exchange to the same extent, maybe revealing also some interesting information about regions that can be more protected from the solvent or maybe involved in a region of high electrostatic potential and so on. So the next step is to try to collect also the CON on the same sample. And you can imagine we were very happy to see that in this case, the increasing temperature has essentially no effect on the quality of the spectra, meaning that we will be able, for example, to recover information about all the amino acids in the protein at a higher temperature in which, I remind you, the HSQC allows us to sample only a tiny subset of the signals. Therefore, these two spectra really are the first ones so we should all acquire when starting the investigation of a new IDP. And we can do it as we all are used to by acquiring first the HSQC and then the CON. But nowadays, most of the modern consoles are equipped with multiple receivers. So why not acquire them simultaneously? Indeed, they are based on acquisition of two different nuclear spins. And it's quite straightforward to encode a pulse sequence variant in which we include HSQC prior to the CON. All we need to do is take care that carbonyls are restored to equilibrium before the start of the CON itself. And this allows then to acquire two spectra in the time needed for one of them. You may say, well, it's no big deal, it's not a lot of time saving, and on this I of course agree with you. But on the other hand, this is information acquired in the same chunk of time, and it may become vital, for example, if we want to follow reactions, for example, to monitor post-translational modification. It will, of course, give more information. Or, for example, it often happens that some samples do not survive in the tube for a long time. So again, it's important to collect as much information in the time they are stable. So I'm just reporting a quick example in this context by showing you spectra, not only on the purified protein as this one, but also on cell lysates in pH and temperature conditions as the previous one, but also in pH and temperature conditions approaching physiological ones. And I was really impressed to realize that these experiments can also provide nice information for alpha-synuclei overexpressed in cells. Okay, so at this point, I think we are convinced that these two spectra are very useful to look at IDPs. And since we do manage to acquire, perform carbonyl direct detection, why not try to also collect additional spectra, just simple 2D spectra, like, for example, the CaCO, in which we correlate carbonyl with a neighboring C alpha, or then also extend this also to the neighboring beta. And here is the result, again, on alpha-synuclein. And at first sight, we may say, it's quite constituted by blobs, right? And we were somehow expecting this because we know that only covalent or mainly covalent contributions to chemical shifts are left, an aspect that actually is responsible for these clusters for specific amino acid types. However, let's look at this in more detail. And so we can identify a region that provides resonance for backbone C-alphas, but we can also see very easily resonances of side chains, in particular of side chains harboring either carboxylates or carbonyl groups. And let's also zoom in one of these clusters. For example, this is the cluster reporting signals from glycine regions. And if we zoom in, we can see that the resolution is sufficient to resolve most of the 15 glycines present in alpha-synuclein. Let's also have a look at one of the peak regions reporting side chain peaks. And indeed here we can monitor 6 resonances of the 6 aspartate residues in alpha-synuclein. Okay, here is the CaCO, and we can at this point decide to plug in an extra transfer step and acquire a CbCaCO. And I have just highlighted as an example one correlation that allows to identify, for example, alanine residues. And of course, all C-alphas will also have their beta, but these will also be useful to assign the side chains of the amino acids. And for longer chains, for example, we will also need a CcCO experiment that will provide richer information. And at this point, we can, for example, transfer the backbone assignment to the side chains and identify and access atomic resolution information on aspartate side chains in an intrinsically disordered protein. So this set of simple 2D spectra can provide a more accurate fingerprint of IDPs and respect to just proton, nitrogen, HSQC, the spectrum we are all used to acquiring. And it can be, so these spectra can be very useful, for example, to monitor interactions of IDPs with protein partners, or to follow post-translational modifications, or accessing also some information about side chains can be useful to figure out which are the driving forces, for example, of liquid-liquid phase separation. And let me give you one example of how we can use these experiments to monitor some aspects of, some interesting aspects for protein function. And I have chosen the example of looking at alpha-synuclein and monitoring how it senses calcium concentration jumps, something that is relevant for the transmission of nervous pulses. And this topic has been investigated through proton, nitrogen, HSQC. So let's see what else we can learn from this set of 2D carbonyl detected experiments. And so here is the CaCO. And of course, if we are, so this is the CaCO. And the carboxylate groups of amino acid side chains will, of course, be the first candidates to sense variation in concentrations of calcium ions, as shown here by reporting the overlay of different spectra acquired upon addition of increasing concentration of calcium ions. And in a disordered protein, all these carboxylates are solvent exposed, so one could expect that they all sense calcium in the same way. But we can tell right away this is not true. Look here, aspartate 2 is not changing, whereas many aspartates, in particular in the final part of the sequence, as well as glutamates, are changing a lot. So we can report these on the primary sequence, and indeed we see major changes clustering in the final part. And these report about the terminal carbon of aspartates and glutamates. And of course, these shifts are larger than those observed for backbone carbonyls. One can go ahead and then also use the CON to monitor the same process, and we can identify specific amino acids changing. And we were also surprised looking in the proline regions to figure out that 2 out of the 5 prolines are also affected by calcium concentration jumps. And a quite surprising aspect, considering that prolines do not have these pronounced metal binding properties. So just wrapping this up, if you map the shifts in the primary sequence, this is the result. And the combined analysis of this information highlights actually 2 motifs in this final part of the sequence as the most affected ones. And these comprise 2 negatively charged residues separated by a proline that has a closed ring. So it somehow confers a bit more local rigidity to these motifs, despite being part of an intrinsically disordered regions. So initial units that are the first ones to sense calcium ion binding. Okay, so I hope this gives a bit of flavor of how we can use this set of experiments to access some interesting information about IDPs. And at this point, we are ready to go ahead and think about the following step: designing a set of multidimensional experiments, either based on amide proton detection or on carbonyl detection, that sort of combine these building blocks and provide a whole set of multidimensional experiments to achieve a sequence-specific assignment. And maybe also we can also think of additional experiments to monitor additional observables. However, we do not have time to go in detail to all of these. And just to briefly show that now this set of experiments comprises a whole suite that is suitable to look at IDPs, together, of course, also with the more recently proposed approaches based, for example, on 15N direct detection or on H-alpha direct detection as initially proposed by Permi and as we heard from Andrea Bodor in the last days. So a whole set of experiments to look at IDPs that, and also when more information is available to look at challenging system, that is of course welcome, as different approaches can be useful to meet different solutions. And some also chapters you can find also in the IDP by NMR book. However, I mentioned I would now like to move on and to show you some examples of how this set of experiments can contribute not only to the characterization of IDPs, but also to the investigation of the so-called intrinsically disordered regions that are actually regions of very complex multi-domain proteins that are intrinsically disordered. And as an example, I show you here CBP. It's, as you see, very large, and it has been studied a lot Indeed, if you go in the protein data bank, you can find the 3D structure of several of the globular domains. But these account only for half of the primary sequence, and the remaining half is predicted to be intrinsically disordered. So we decided it was time to try to access some investigation, because these were considered just as flexible linkers. But of course, it would be a waste if nature had just used all this information just to produce some ropes connecting the otherwise functional globular domains. And here are the ones that we have investigated so far. As you see, they're quite large and very protein rich. So let me show you, for example, the personality of this fourth intrinsically disordered linker. Here is the two spectra that now we can consider some kind of the ID of the protein. And of course, in this case, with this complexity, it was only through the combination of HN and carbonyl detected experiments that we could complete the characterization of the protein. By plotting chemical shifts and comparing them to predicted random coil ones, we can obtain these secondary structure propensity plots that indicate the presence, for example, here of 2 alpha helices, where this parameter is positive. And interestingly, the prolines are actually distributed in the remaining region. So somehow they even have an active role in discriminating separating the alpha helical regions, as known from their role as helix breakers. One can then also, of course, collect, for example, 15N relaxation rates, which do confirm that helices are less mobile with respect to the remaining regions, or also other kinds of observables to characterize these structure and dynamic properties. And at this point, we realized that most of these IDPs do have their proline resonances that are well separated for what concerns the 15N dimension from the remaining resonance. So we thought, since it's maybe not in all cases we will be able to really collect all the experiments, why don't we try to use this carbonyl detection to access only the information in the region that is essentially inaccessible with amide proton detection. And so we designed these super simple experiments in which the major difference consists in introducing a 15N band selective pulses to select the proline resonances. And then experiments become more simple, but if you zoom in this region, this looks superficially like HSQC of a small protein. Instead, is only reports the proline resonances in this ID4 segment. And as you see, there are a variety of motifs that deserve to be studied. And even we can monitor different regions for different kinds of proline pairs. We can also then go ahead and, for example, design experiments to monitor 15N relaxation to characterize them in detail. And for the moment, what I would like to draw your attention to is that actually, respect to all other amino acids, these 15N relaxation rates of prolines are smaller. Of course, expected, no, because they do not have an amide proton, so they lack this dipolar interaction. But good news, because if we wanted to evolve to larger systems, these narrow line widths will actually be an important feature. And now I would like to conclude by showing you one recent example of our studies that was stimulated by this virus that we deal with since a couple of years. And so at the onset of the pandemic, we said, how can we use these tools to give a little contribution to science in this field? And we decided to focus on one of the protein that is richest in disorder. After chatting a bit with our friend and colleague Vladimir Uversky, who provided us these nice plots that indicate how different disorder predictors predict these proteins. So if you see 1, it's total disorder, and 0, total order. And as you see, in some regions, these predictors do not agree. So we thought it's time to provide some information, experimental information. And actually, the structure of the 2 globular domains was already known from previous viruses, and it has been determined, but no atomic resolution information about the linkers was available. So we decided it was worth to invest our energies into looking into this, and started by looking at a smaller chunk of the protein that, however, comprises the known RNA binding domain and the 2 adjacent flexible linkers or disordered regions. So these are part of the primary sequence. The spectra, the first 2 spectra that we acquire on these protein now also reveals the presence of a globular domain from these well-dispersed resonances in the HN-HSQC. Here it's a bit of a mess, but if you go higher in contours, you can clearly detect the resonances from the disordered linkers. And how about the CON? The CON has 2 blocks that act as sort of a relaxation, strong relaxation filter, the CON transfer delays. So essentially, the only signals we can monitor are those from the disordered linkers. However, this is interesting because it really simplifies our work of assignment with respect to this kind of spectra. And these spectra were so nice that we used them for the practicals for the students, because as we all experienced, it was not easy at all to teach during the pandemic. So at least we thought we could provide something that was interesting for them. And the first spectrum we all acquired for assignment is the 3D-CB-CA-CON, in which essentially we correlate the nitrogen of 1 amino acid with the carbonyl. So one of the planes is the CON itself. And in the orthogonal plane, we have essentially the CaCO. And here is the experiment. Here are the experimental data in which I have just reported the CON plane for clarity. And here I have reported the primary sequence of the protein, where in white I have highlighted the flexible regions. And which would be the first region to start from? I mean, one thing we know for sure is that these peaks in the bottom will derive from proline nitrogens. So we can go ahead and fish in the primary sequence where are the prolines and pull them out of the white fragments, the ones predicted to be disordered. And as you see, we have 7, and here we have 7 peaks. So good news. And then remember, these peaks in the orthogonal dimension will report information about C alpha and C beta of the previous amino acid. So let's go ahead and pull out the orthogonal planes of this 3D spectrum and see what happens. And when we arrive at this 15N frequency, these are the resonances that appear. And I mean, if you have experience with this, you have already realized the assignment. This is a clear signature of a threonine amino acid. If not, one can just go and look in the BMRB about chemical shifts. And so just from this quick look, we assigned together one of the resonances of these linkers of this protein that have never been assigned before. And then let's go up, and the next plane that we find has this signature that immediately can be assigned to a serine-proline pair. And so we can continue this game and go up. And this, for example, belongs to an arginine just from the chemical shifts of the peaks. This belongs to a leucine. And for example, this is very clear. This is the signature of an alanine residue. So just by playing together with this simple game, we managed to assign all of the resonance in the proline region, except these two glycine-proline pair, for which some ambiguity still remains. Of course, by acquiring a more extended set of experiments, we can complete the assignment for the rest of the proteins and deposit it in the BMRB. So this is now, of course, available to calculate our secondary structure propensity plot that reveals here partially populated helix, for example, and that is available for the community to investigate in more detail this protein, as is being done by a variety of groups nowadays. And let me just conclude by showing you some of our results that actually tell us, by monitoring the interaction of these two, of the RNA binding domain and of the same flanked by the two linkers with the RNA, these experiments tell us that the linkers do matter, as they actually contribute to an increased affinity of the protein with RNA, monitored either through EMSA and through, of course, NMR. And by applying these multiple receivers, CON, HN spectra, acquired simultaneously, we were able to see that not only the known flexible loop of the RNA binding domain is, of course, involved in interaction, but that also two flanking regions, actually also very rich in positive charges, are very important in the interaction itself, as well as some remote regions in the primary sequence. So I hope I have given you a flavor of actually which are the important ingredients of NMR experiments to optimize them for the study of intrinsically disordered proteins. And I really hope that these will be widely used by the community to have a better idea of the general properties encoded by disorder in proteins. And as one can tell by, for example, scrolling through this sort of protein gallery, in which there are several kinds of proteins can be studied that range from simple ones that, however, for example, have a number of residues of the same type and still are challenging, to alpha-synuclein that we know, or to proteins, IDPs of increasing complexity, such as saccharin, one of the first ones we studied, or osteopontin, in which we collaborated with Robert Conrad, or finally some viral proteins, for example, E1A, again characterized by a quite complex primary sequence, or this very large protein chunk that we studied together with Sonia Longhi. And as I mentioned, we can also study linkers of complex protein. Here a nice example is provided by the N-terminal region of the androgen receptor that is involved in the onset of poly-Q diseases, as one can tell, going to a variant with a higher number of glutamines. And by, for example, the example of the linkers of CBP, this is the one I showed you, but it's not the only one, as I mentioned. And for example, here is the third linker, again, quite extended and actually with a quite challenging amino acidic composition, and so with its own personality. And finally, all the way to now going to the next step, that is studying the flexible linkers within a more complex construct to see their synergic action with respect to globular domains. And what I'm fascinated about is that these studies are beginning to reveal a large number of modules encoded by disorder that have not been reported, of course, in the protein data bank. So maybe we can really contribute to expanding our knowledge about the protein function. And with this, I cannot end without briefly mentioning the key persons that I worked with in the years, and also reminding you that to keep an eye on the various projects of access to our research infrastructure, in case you would like to come and try out some of these experiments without setting them up on your systems. And thank you for your attention.
I'm not sure how much you can hear the clapping over the audio, but thank you very much for that really beautiful tutorial and all the intrinsically disordered proteins you've been looking at. I believe we have time for one quick question before we move on to the next tutorial. If there's a question, go ahead.
I cannot hear much, Joanna, in case you repeat the question, because...
Oh, they just stepped to the microphone, so they'll ask the question.
Okay.
Now.
Hi, do you use longer recycle delays for these carbon detected experiments?
Oh, of course, it's a bit longer than protons, but it's not so tremendously longer. You can use for IDPs, highly flexible IDPs, something like 1.5 seconds or 2 seconds. This is what we generally use when we focus on carbon detect experiments. On the other hand, there are many variants of the experiments where you can actually also exploit proton start and transfer the proton polarization to carbons, what we like to call exclusively heteronuclear experiments, because protons are only used as a starting polarization source, while only heteronuclear spins are labeled in all the experimental dimensions. And so, of course, in that case, the D1 is exactly the same as one would use for sort of more normal proton detected experiments.
All right. Thank you.
Thank you. So in the interest of time, we're going to move on to Danielle's talk, but thanks again, Isabella. That was beautiful, and have a good
Thank you, Joanna. So enjoy the boat race. I will miss it a lot.
Yeah.
Maybe, I don't know, I should mention that last year I sunk the boat.
Well, hopefully there'll be enough duct tape this year. Okay, so
okay, bye-bye.
Bye. Our next speaker is Danielle Lorenzen, who is going to tell us about strategies for introducing oxygen-17 and what can be learned from oxygen-17. And Danielle, can you unmute yourself? Danielle, can you hear us?
Yes, I'm here.
Oh, there you are. Great.
Yeah. Okay, thank you, Joanna. Good afternoon, everyone. So the purpose of my talk is to give you a feel of some of the recent directions the community has been working towards to reach higher sensitivity for oxygen-17 NMR spectroscopy. And I'd like to associate to this work the whole group in Montpellier, with whom we've been working as chemists presently, but also in the past with former colleagues, to try to gain more sensitivity around this nucleus. So why focus on oxygen? Because it's everywhere. In mass, it is the most abundant element at the surface of our planet, where you can find it both in living organisms and inert matter. And from a chemist's perspective, it's present in all major bonding environments, whether they are covalent ionic coordination or hydrogen bonds. So potentially, if you want to understand the structure or reactivity of a given system, there is a real interest in being able to focus on the oxygen local environment. And this can be done by NMR, by looking at oxygen-17, which is the only nuclear spin, which is the only isotope to have a nuclear spin not equal to 0. And while the first spectrum was recorded back in 1951, over the years, this spectroscopy has known many developments, starting off with a study of small molecules in solution, polyoxomedlates, and progressively shifting towards more complex systems, going from glasses to proteins. Now, it turns out that oxygen-17 NMR is interesting as a technique, notably because of the very wide range of variation of its NMR parameters. The chemical shift range exceeds several hundreds of ppm for organic molecules, as illustrated here, with alcohols on the one side and ketones on the other. But also, they also have a wide range of variation of quadrupolar parameters, because oxygen-17 has a spin 5/2. You can measure the quadrupolar complete constant CQ, which can reach up to tens of megahertz. And these wide ranges of variation also hold for inorganic compounds, as illustrated here, with this time the chemical shift and the quadrupolar parameters plotted vertically against the bond ionicity. This was an attempt a few years back to understand the meaning of these parameters. And if we just focus on compounds in which the oxygen is surrounded by titanium, you can see that it can cover over 800 ppm. So intrinsically, you have this huge range of chemical shifts and this very broad range of variation of quadrupolar parameters. But also, progressively, it's been shown that you can perform high-resolution NMR experiments through 1- and 2-dimensional correlation experiments to look at amino acid and peptides, as illustrated here on a proton-oxygen correlation study, to look at hydrogen bonding, notably in crystals, but also, as very nicely shown yesterday by Rick Dorn from the Rossini group, through boron-oxygen correlation experiment to study this bulk structure of classes. Now, there is one main issue, which is up here. It's the very low natural abundance of the NMR active isotope. And this means that if you're running experiments under what I would say standard basic NMR conditions, you will need large amounts of sample and very long acquisition times if you're carrying out the study at natural abundance. There are just two illustrations here in the field of solution NMR and solid state NMR, where you can see that in both cases, large amounts of samples are required to reach a concentration of 1 mole per liter, for example, or to fill a 7.5 millimeter diameter rotor, and very long acquisition times. And this is why the community, because of the high interest of oxygen-17, has tried to push the research in directions to reach higher sensitivity. And this can be done through different means, either through isotopic labeling or through the development of pulse sequences, which will help you boost the sensitivity, for example, by playing on the satellite transitions with so-called double frequency sweep pulses, for example, or through instrumentation with the access to high and ultra high magnetic fields, like the series conducting hybrid magnet at 35 Tesla, or the use of cryoprobes, and of course, thanks to DNP. But if you really want to go above just one order of magnitude gain, well, the main two techniques to go for are isotopic labeling and DNP. And for today, I will focus on the former, because the advances we can make along this direction can really help also make progress along the others. And my feeling is that this can really push further oxygen-17 NMR spectroscopy. So now let's focus a bit from a chemist's perspective on the oxygen-17 isotopic labeling. And I will first talk about some generalities around this isotopic labeling before focusing on one of the methodologies we've been pushing forward in Montpellier, which is based on mechanochemistry. So when you think as a chemist of performing oxygen-17 labeling, the first thing you go is to the suppliers and you check what's available. And it turns out that I would say there are less than 20 compounds commercially available. They're not all shown here, but basically there are very few sources you can purchase, and they are not all in stock. And moreover, when you look at the last column here, well, it turns out that often they are sold in small quantities. Typically, the labeled water is sold in these small 1 millimeter vials, and the cost can be high when not extremely high. So for today, we'll focus mainly on these two precursors, which are those which the community has the most used to perform the oxygen isotopic label. So O2 gas and H2O17 can be purchased either as a small vial as shown previously, which is very easy to manipulate, or in a cylinder of a volume of 1 liter in the case of O2 gas, which requires specific training. Now, as chemicals, they are very different. In this case, you can do, for example, oxidizing reactions, whereas in the other, you can do hydrolysis reactions. Yet, despite these differences, the common strategy which has been developed for the isotopic labeling has been to start from a compound which you can label in presence of one of these enriched precursors, NO17, using an equilibration reaction where non-labeled oxygens will progressively exchange with labeled ones, or by performing a quantitative transformation where you start from a precursor, which will then become enriched in O17 upon exposure to these compounds to form your compound of interest. Now, to be more specific, let's just start with a first example, silica. There are here the comparison of 2 strategies where the isotopic labeling of silica can be performed in presence of O2 gas, for example, at high temperature over 24 hours, or by hydrolysis of silicon tetrachloride under inert conditions in diethyl ether solvent to form silicon dioxide labeled, silica labeled in oxygen 17. And beyond silica, a wide range of other organic and inorganic compounds can be labeled in a similar way, using what I will call a post-enrichment strategy, because you have pre-prepared your compound of interest and you post-label it in O17, or a direct enrichment strategy, because you synthesize directly your compound labeled in O17 from purposely chosen precursors. And here are just other illustrations of mixed metal oxides, which can be labeled by post-enrichment, for example, or molecules like benzoic acid, which can be labeled in O17 by a direct enrichment strategy. Now, there are many different other examples along these 2 lines in the literature. 2 things to bear in mind. The NMR signatures you'll be getting for a given compound will not necessarily be the same, depending on what strategy you chose if you're not carefully paying attention to your reaction conditions. This is just illustrated here for the case of a polyoxomelate, PW12043-, which in one case was labeled by a post-enrichment approach by exposure to enriched water, whereas in the other, it was synthesized, labeled in O17, started from labeled water, but also other precursors which had been pre-labeled in O17. And in one case, it turned out that the central phosphate of this Kagan structure had not been labeled in O17 through this post-exchange because the PO bonds within the time frame of this experiment had not had time to be enriched because they are at the center of the anion. Whereas in the other case, because the synthesis proceeds directly from fully labeled precursors, all atoms were enriched. Similarly, the other thing you have to keep in mind is if you're taking one enrichment strategy, for example, the post-enrichment, your oxygen 17 signature might differ depending on the nature of your labeled precursor you will be using, whether it is water, for example, or oxygen gas. And you have here just an illustration on the study of Ceria nanoparticles, which could be enriched by a post-enrichment strategy, starting from enriched water in one case, or dioxygen gas in the other. And you have a comparison of their oxygen 17 solid state NMR spectra shown here, where you can clearly see that in the case when water was used, a much larger signature of the hydroxyl groups at the surface was observed. Now, more generally speaking, let's have a look at all these different labeling strategies. And what we can see is that there is a common feature. Generally speaking, we can say that for the post-enrichment approach, because you are dealing with a thermodynamic equilibrium and you want to have something which is enriched and highly enriched in O17, you generally use an excess of the labeled precursor. And this turns out that it can be extremely costly. If you think of it, if a single vial of O17 labeled water costs up to 2,000 or 3,000 euros. Well, if you're already using a third of that just to label a single molecule, that means your experiment will come to a cost. The other comment we can make about this strategy is that because you want to be sure you have reached this thermodynamic equilibrium, very often the reactions are long. They can last days, when not weeks, in some of the described protocols, and they are performed at high temperatures. And in some cases, it turns out that this could be a disadvantage if your compound is sensitive to temperature. However, the pros would be that they are directly applicable to the compound you're interested in, and also there are no byproducts to eliminate. On the other side, for this direct enrichment strategy, among the cons, we can say that actually you often start from very reactive precursors. This compound here, or generally chlorinated compounds, can be hazardous to manipulate, if not potentially toxic. And often you have the production of other byproducts, which you will be needing to eliminate. So this is something to keep in mind in this type of approach. Yet, it is interesting to see that all the oxygen you are introducing, or most of the oxygen you will be introducing, is meant to react to form your labeled compound. So potentially, you will be using a smaller amount of enriched material to label these compounds in O17. But more generally speaking, when we had an overview of all the protocols which were being used in the literature a few years back, it appeared to us that they were unattractive on a general basis, either in terms of time or in terms of the reaction condition used, or simply in terms of cost. And we and others in the community have tried to push forward other types of approaches to improve the isotopic labeling in O17, because we're now at a stage that we know the spectroscopy works. So now let's make it available to a broader community of chemists. And so the idea is to try to use what I would say a green chemistry approach, meaning work under more mild conditions, lower temperatures, greener solvents, work with faster reactions, potentially which would work in less than half a day, workup included, with a lower consumption of the O17 labeled compounds. And importantly, a lot of the early protocols were missing a lot of experimental details. The goal at the time was only to get an O17 NMR spectrum. And so we really need to put some effort here for others so that the protocols can be usable and reproducible. And so starting from our favorite enriched precursor, which is the easiest to manipulate, there have been many developments in the past 5 years, I would say, around the labeling on one hand of organic molecules, including biomolecules, such as the fatty acid family, which had not been looked into so far, and also efforts around amino acids, including in their FMOC-protected form, in order to perform peptide synthesis afterwards. And on the other hand, in terms of materials, there have been extensive developments for the isotopic labeling of porous materials such as zeolites and MOFs, as well as coordination networks under much more mild conditions than what had been performed so far. As of today, I will focus on one of the approaches we can use, which will allow us to tackle these different criteria in one go, which is mechanochemistry. And this is what I will be presenting to you in the second part of this presentation, starting with some generalities, as you may not all be familiar with this synthetic technique. So in mechanochemistry, you start from solid reagents, which are introduced in a reactor in the presence of walls. And the medium is ground at several tens of hertz. And this allows to reduce the size of your particles, mix them efficiently, and make them react at their interfaces. And potentially you reach very high kinetics simply because you have no bulk solvent. So the reagents are there at very high concentrations in your reactor. Under the different movement of the beads, the particles will be undergoing different types of forces, which make them react at their interfaces. And this synthetic route has been developed and is being pioneered nowadays for the synthesis of inorganic materials, but also organic molecules, coordination polymers, and different types of MOFs, as well as co-crystals. Now, when you think about the different synthetic parameters, you can vary when you're doing a reaction in mechanochemistry. There's the type of milling jarring system, the amount of powder in your reactor, the extent of filling of your jar, and a number of other parameters. But what we were really interested in is that in a number of cases, it was shown that you can add a very small amount of liquid, which will assist in the diffusion processes between the particles and generally accelerate the kinetics of the reactions. This liquid grinding assistant agent, is introduced typically in the amount of less than 1 microliter per milligram of sample. And the idea here was to use not any type of liquid, but oxygen-17 labeled water, which would be introduced in the microliter quantities, typically less than 1 microliter per milligram, and which would also play the role of a reagent to label your compounds of interest in this isotope. From a chemical perspective, how can we use water in mechanochemistry to perform isotopic labeling? So far, we've used it in 3 different ways, either by performing an equilibration type of reaction, as described previously, but this time under mechanochemical conditions, or to perform a hydrolysis reaction from a precursor which will have be purposely selected and which will react quantitatively in presence of water, or to perform a hydration reaction. If you imagine, for example, that you wish to study the water molecules in your final compound, you can introduce them in your material through mechanochemistry. And now I will walk you through a few examples as to how this technique has been applied in the labeling of inorganic and organic compounds. So in terms of inorganic compounds, a wide variety of hydroxides, oxides, but also hydrated species have been enriched in O17 using mechanochemistry. And these are the types of reactions which have been involved in each case. Those are the ones I mentioned just previously, as that is an equilibration type of reaction for the hydroxide. For the oxides, it's hydrolysis and recondensation going on during the ball milling. And for the hydrates, different approaches are possible, either a hydration reaction or an equilibration. If we start with just one example, in the case of the hydroxides, it's very simple. You start from your metal hydroxide, typically 60 milligrams, introducing the jar in the presence of a bead and in the presence of just 1 drop of O17 labeled water. Perform the milling for a short period of time, typically 15 to 30 minutes, and then you recover your compound, which is on the walls of your reactor. You scrape it out, and you can characterize it. And here you have the illustration of what we obtained in the case of calcium hydroxide. After this short milling time, the powder pattern is essentially the same as before the milling. However, what's very nice is that the compound is nicely labeled in O17 with this solid state NMR spectrum recorded in just 2 hours on a 600 megahertz NMR instrument. So if you think of it, in just 30 minutes, using mechanochemistry, it is possible to label a compound like calcium hydroxide in O17. And a similar approach can be used for other types of hydroxides, which can then be converted into the corresponding metal oxides under standard heat treatment conditions with an inert atmosphere to avoid using your isotopic label during the conversion step. In doing so, we were actually able to quantify the extent of labeling in the final oxide by comparison with a natural abundance measurement we performed under similar conditions. So this is just an illustration for the hydroxides. However, many compounds of interest do not come under the form of hydroxides. And that's one of the reasons where we tried to find other ways to label metal oxides. And the general idea was to start from oxides themselves, perform their hydrolysis or partial hydrolysis using mechanochemistry, and then heat treat them back under inert atmosphere to be able to recover the labeled oxide. So the key point here was to what extent it was possible to perform this type of hydrolytic step on different types of oxides, which are of interest to the synthetic community. And to go back to one of the very early examples of this talk, in the case of silica, if you start from non-labeled silica, in just 5 to 15 minutes, it is possible to enrich it in O17 using one equivalent of O17 labeled water. The powder is very easy to recover from the reactor, and it is possible to perform in just a few hours high-resolution solid-state NMR experiment on this labeled material, as shown here, with spectra such as the triple quantum MAS experiment or 2D proton-oxygen correlation experiments. So in comparison to some of the previous silica protocols I had mentioned, requiring silicon tetrachloride or SiO2 exposed to O2 gas, this is a very attractive strategy for enriching this type of material. Just two warnings, however, in this type of chemistry, you have to be very careful in the choice of your starting material. I'll just give one illustration of this in the case of zirconia, where we had two types of zirconia sources with very different crystallinities. And it turns out that while using similar milling conditions in presence of one equivalent of labeled water after just 1 hour of milling, one of the compounds got enriched in O17, while the other stayed unenriched. And the only signature we were recovering was actually that of the rotor, the zirconia rotor, which comes out in the same position. So the nature of the starting material is important. And the work we've done on oxides, especially silicon, aluminum, zirconium, and titanium oxides, started from compounds which were available in a porous form as particles agglomerated one with the other, and not highly crystalline as the sample shown here, to favor the surface contact between the labeled water and the particles of your oxide. So a large variety of inorganic compounds can be labeled by this technique, and others have used it as well to make functional materials such as mixed metal oxides, which can be used as cathodes, or zeolites. How about organic molecules? In the case of carboxylic acids, most unfortunately, you can't just take your carboxylic acid, put a drop of water, and enrich it in O17. In this case, you have to perform a hydrolysis reaction on a purposely selective activated molecule. And here we've used two approaches. The first approach is to start from a carboxylic acid and activate it by mechanochemistry using this reagent, carbonyl diimidazole. Once you form this activated intermediate, you can back hydrolyze it with a stoichiometric amount of enriched water to form your labeled carboxylate, which after a workup step can be isolated as a carboxylic acid enriched in oxygen 17. Important note, we test these protocols with non-labeled water, optimize them with O18 labeled water, which is much cheaper, and it allows us to make sure that our isotope label is properly introduced in the molecules before we apply the protocols to O17 labeled water. And other side note, because of the proton hopping in the solution when we're isolating the molecules, of course, we have the two forms which are present in the solid state in the isolated material. This type of strategy and this synthetic approach was used on a wide variety of compounds, including fatty acids, both saturated and unsaturated, which could each be isolated as few products with high synthetic yields and high enrichment levels, and with protocols which are reproducible, scalable, fast. In just half a day, you're able to label your fatty acid in O17, and relatively low cost because you can produce now approximately 300 euros, 1 gram of O17 labeled oleic acid. And to illustrate the O17 labeling of this molecule, here are just some of the characterizations we've performed on it by mass spectrometry, for example, where you have the comparison of the natural abundance and the labeled molecules shown on this side, or by solid state NMR spectroscopy under magic angle spinning conditions. So the first strategy we were using was a two-step protocol. Starting from the carboxylic acid, you activate it, and then you hydrolyze it in presence of O17 labeled water. Yet some of the fatty acids were not available commercially as the acids, but as esters. And so we developed another approach, which consists in starting directly from esters and hydrolyzing them by ball milling to form the corresponding acids after the proper workup. The key point here is that the labeled water is introduced in the jar in presence of a very strong base to generate labeled hydroxide ions, which will perform a saponification on your ester to form this enriched molecule eventually. Again, these protocols are tested in three ways, starting from non-labeled water, then O18 labeled water, and finally O17 labeled water. And they could be applied to a series of polyunsaturated fatty acids, which were all isolated pure and high yields with high enrichment levels. And one of the major advantages here is that it's just one step. The reaction is fast. In 30 minutes, the saponification is done. The ball milling is performed under ambient conditions, and the reactions are reproducible, low cost, and suitable for also polyunsaturated fatty acids. Here are just some of the characterizations which demonstrate that this saponification approach works in the case of one of the molecules, eicosapent pentaeonic acid. And you have here the characteristic of the labeled compound, the demonstration by mass spectrometry that it can be labeled in O17. And you can also play with the O18 labeled species because you have these isotope shifts in carbon-13 NMR. So it's another way to check that your protocols are working by looking at your carbon-13 NMR spectra in the carboxylic region. So overall, using mechanochemistry, we've been able to label a variety of molecules containing carboxylic groups using two synthetic approaches, whether these molecules are ligands, organic molecules like ibuprofen, protected amino acids, and fatty acids. And now, if I still have a little bit of time, I'll move on to a few experimental aspects related to this technique so that you can know where to start if you want to go into it. So there are many questions here. You might ask yourself, what milling equipment, what type of jar use, what duration use for the milling? How should I fill the jar? How should I recover the sample? Are there any hazards I should be aware of before starting? And so this is a type of questions for which we've developed know-how over the years now. And if we start off with the type of milling systems, well, if you look at what's available, there are mixer mills, which allow you to mill either by shaking horizontally or vertically. And then you have planetary mills, which have a different type of movement of your reactor and beads around two different axes. And it turns out that in our case, we've used all types of milling equipment to perform isotopic labeling. And you have here the typical quantities of reagents we've been able to use and the typical quantities of water introduced in the reactions for performing these isotopic labeling reactions, with in some cases, scale-ups which could be performed for some of the carboxylic acids to then perform other types of synthesis in terms of organic or materials chemistry. It's important to note that other groups who have started to use isotopic labeling for ball milling have had other equipment available in their laboratories, and it works as well. And these are just a benchmark of the types of quantities of powder or water they were introducing in their reactors. But for me, the bottom line here is basically if you have a milling system in your lab, well, all the milling systems available will work for the isotopic labeling as far as this type of experimental technique works. Now, the second important point are the jars. Depending on whether you're playing with a mixer mill or a planetary mill, and depending on the brand of your instrument, the jars will have very different designs in terms of their volumes, in terms of their geometry, and also in terms of the way they close up. And here is just an illustration of one of the jars we have, which has this rubber O-ring, which seals the top from the bottom. Others have a screw top. And others come in small pieces, like these jars from the planetary mill, which actually come in all these little bits, which have to be assembled before performing the mill. So you have to be aware of all these different parts, because the closing system in particular, you have to be careful with if you don't want to have any leak during your isotopic labeling potential. The second point to be aware of when you're thinking about the jar is the material of the jar. There are many different which are available, and we've used several of these for different reasons. Most common being stainless steel, zirconia, which have different density and different properties. In terms of their chemical inertness, I would say that you have to be careful for stainless steel if you're dealing with acids, because you can potentially corrode it with time. One important point to bear in mind is that we are performing a mechanical reaction. This means that there will be some wear of your reactors over time, especially if you're not careful and if you're milling under too harsh milling conditions. And there have been, for examples where you can recover chromium or iron impurities in the case of stainless steel, which can potentially be advantageous if they are not in too strong quantities, because they can have interesting relaxation properties, interesting relaxation properties within your compounds. And in other cases, they can give additional signals, for example, in the case of zirconia, potentially. There are other types of milling jars we have also been using, for example, for organic molecules or for other types of studies through operando analysis of the reaction media. These are generally more fragile and not necessarily adapted to organic solvents, so they have to be used potentially more carefully before you're performing your reaction. But there is a wide variety of different systems, and so basically you have a lot to play with. Important point to bear in mind is these jars come with a cost, and this is why we use them with care, to make sure that we're not going to destroy the jar completely in one milling reaction by using much too harsh milling conditions. And so I like to put in these prices for the students, just so that they're gentle in their milling conditions and that they can use their jar as long as possible for many, many different reactions. Second thing, so now you have the jar. How would you fill it? So the rule of thumb given by the suppliers is 1/3, 1/3, 1/3. So basically 1/3 of vacuum, 1/3 of solid reagents, and 1/3 of beads. We're actually quite far in most cases from those conditions. As I was mentioning, sometimes we just have 60 milligrams of sample plus 10 microliters of labeled water. And this is why, because we are much lower, we use less material because we don't want to engage too much labeled water. But we could potentially get more contaminations because that material will be coating the full jar. So this is why sometimes you have to be very careful in your milling times. If you're milling too long, you can severely increase your contamination. The other important point to bear in mind is if your jar is too full, or if the number of beads is not adapted, the mixing may not be optimal, and you may be getting unwanted reactions or a non-homogeneous mixture. And this is one of the examples we had when we were trying to enrich stearic acid using the planetary mill. So you have a lot of beads in this case, and some of them had these streaks at the surface, which are characteristic of and these circular marks, which are characteristic of a rolling effect. And when we performed characterization by IR spectroscopy of different parts of the reactor, we were able to see that the advancement of the reaction was not the same in all the bits. So we had to change the milling conditions to avoid this. Milling time. You have to choose it so that your reaction is complete. And you have to choose it so you have a good enrichment level. And in the case of oxides, we've seen in a number of examples that if you increase your milling time, you will have a higher enrichment. However, as mentioned previously, the longer you mill, the longer also you will have this mechanical action on your reactors. And so you may potentially come out with colored products if you're trying to play it too long. You will potentially be damaging your equipment, and the equipment is expensive. With time, you might be heating progressively your medium, And in some cases, if you're not interested in it, maybe you might be amorphizing your material, which could be potentially problematic. So far, in terms of milling times, we've been using typically between 1 minute and 1 hour for inorganic compounds and up to 3 hours for organic molecules, and carefully looking at the material after different times, sampling it to follow through ex situ analysis, the evolution of the reaction medium to make sure that we were getting the compound we wanted with the minimal contamination and the optimal labeling under the conditions. The key message to keep here is make sure you check your protocols first with normal water and O18 labeled water, just so you're confident before you switch to the O17 labeling. Just as a side note, it is possible to look at what's going on inside, not using these types of milling jars, but jars which are transparent to the ramen bean, for example. And there is a whole other range of experiments which are being performed by the community and that we have started to adapt for O17 labeling of specific phases, which allow us to trap different intermediates and then study them by solid state NMR. Last point, so once you've done your milling, how do you recover your compound? In the case of inorganic compounds, you have to scratch in some cases. The key message we generally have in the group is to do it gently, to try to make sure that you'll have a good yield, but also a good sample and purity, but also you're not going to scrape your jar too harshly. And in terms of organic compounds, it will really depend on the texture. In some cases, after performing one of the millings on palmitic acid, PA, we had an oily type of texture. And then sometimes we add water to transfer the medium and then perform a workup. So it can really depend on what you're dealing with for organic molecules, but it's more easy, generally speaking, because you can just dissolve them. And last but not least, we're chemists, and so we're careful about what we're doing. What we've described seems simple, but you have to be careful. Does your reaction involve the release of gas? It turns out that for the CDI activation and hydrolysis I described for the labeling of carboxylic acid, you can produce CO2. So you have to be careful and calculate what potential buildup of pressure you would have in your reactor. You have to be careful if the reagents you're introducing are potentially oxidizing or explosive, and beware of potential temperature increases during the mill. If in doubt, start on small quantities, use short milling times, check the temperature after milling, open the jar under a fume hood, or even put the mixer mill under a fume hood if you're extremely scared of what may go on. So this wraps up what I wanted to say. There are many reviews on oxygen 17, generally speaking, and sensitivity gains. And once again, I'd like to thank our group in Montpellier. We've just moved to a new building. You're welcome to visit us, and we're happy to share some of our know-how on this isotopic labeling, and I'm happy to take one question if there's still time.
Thank you very much, Danielle. I think we have time for a quick question. If anybody wants to step up to a microphone.
Very nice talk. I have a question about the temperature increase and just controlling temperature generally. Do you have an idea of how hot or like locally how hot it can get inside of one of these ball mills? And if it's possible to keep temperature down or intentionally increase temperature? It's like temperature control a thing, I guess.
So it's a very good question, and it's a very hot topic, if I may say. So you can monitor the external temperature of the jar using a thermal camera, which is positioned just outside your jar. The temperature increase will largely depend on what you have inside, because the physical chemical properties of all powders are different. It will depend on your milling frequency. It will depend on the type of reactor material you're using, etc. If you take one example, if you mill terephthalic acid alone, the external temperature of the jar rises by 10, 15 degrees over the milling time of I would say 15 minutes or something like that. That's all we can say. how can we control the temperature? So there are commercially designed equipments which are available to go down in temperature. There's cryomills. To go up in temperature, I know Wretch just came up with a new type of design for heating the milling jar at given temperatures in a controlled way. However, most of the work in terms of heating and cooling is done by different groups throughout the world and with many different types of designs. And I'd be happy to discuss that separately later, just because it's something we're looking into too. So,
Thank you.
Okay, one more question.
Hi, Danielle, great talk. This is Rick Doran. I was wondering, for when you're oxygen labeling the fatty acids, how hydrated do they stay afterwards? Like, are you able to completely dehydrate and remove all the excess water afterwards?
So when you label the fatty acids, so there's an activation and then a hydrolysis step, and then there's the workup. And in the workup, you can do it in two ways. It's either a precipitation or you do an extraction to an organic phase because they have a long fatty acid chain. And in both cases, whether you precipitate them or extract them, the compound you isolate, you dry under vacuum. So you don't have any O17 labeled water left into your final material.
Okay, great, thank you.
Okay, please join me in thanking Danielle once more for a great talk. For our last tutorial of the session, we're going to turn to hardware, where Jason Stockman will give a tutorial on a practical guide to building and safety testing RF coils. Okay, Jason, we see you up on screen.
Okay, can you hear me all right?
Yes.
Okay, let me share my screen. All good?
All good.
Okay, thanks for the invitation to give a tutorial on RF coil array building. I'm going to focus on receive arrays, and I have a consulting relationship with Neuro42 to disclose. I'm coming from the in vivo MRI world, and most of my experience is with building what we call massively parallel RF receive arrays. These are multi-channel arrays of detectors which each independently receive signal from a localized patch of tissue, and we put them on 3D printed formers that are patterned to different parts of the body. So you can see here a chest array for cardiac imaging, a few examples of brain arrays, a primate array here. And so my bias in this talk is talking about what I know best, which may be a little bit outside the milieu of some of the traditional hardware used at ENC, but I wanted to give a sort of in vivo perspective on building this hardware and a practical guide so you can go out and do it yourself. So with that caveat, first, why do we care about using what I called massively parallel receive arrays? So I'm going to motivate that with a few slides. Then I'm going to dig into the basics of the circuit theory and some simulations of coil performance. This will include the really fundamental metrics of performance like tuning matching, pin diode detuning, preemptive coupling, and common mode blocking. And I'll touch on some fundamentals of the Smith chart in order to explain these concepts. And then we'll attempt to do a live coil tuning demo on the bench if the AV cooperates. So first, why do we care about using parallel receive arrays? One motivation is to pattern coil elements over the body to improve coverage of the anatomy of interest. And by using lots of loops in parallel, we increase the channel count and we're able to pattern the loops close to the body to boost SNR. And we always want more SNR in MR applications. For in vivo imaging, this lets us push the voxel size smaller to depict body structures in finer detail. But you get more than that. By using many independent degrees of freedom to receive the MRI signal, you can actually get higher acceleration factors during reacquisition, method so-called parallel imaging. It reduces the scan time, it can limit motion artifacts, mitigate distortion and blurring in equiplanar acquisitions, and has other benefits. So, okay, first, if we think about coverage in SNR, let's take the case of sensitivity or SNR as a function of loop size. If you take a single 30 centimeter loop, you're going to get a lot of coverage, but less sensitivity. If you use a smaller 8 centimeter loop, if you go to the center here, you will get more sensitivity and it will fall off more quickly. But by patterning several of these loops next to each other, you extend that region of high sensitivity with an array of 8 centimeter coils. And so this does better than a single large coil further away. So how do we assess SNR? Well, we're interested in the B fields and the E fields generated by a loop in a sample. In my case, it's usually the body. The signal scales with the B1 minus field, the receive sensitivity of the coil. And the noise can be modeled as an equivalent resistance. That resistance has 3 components. The first is the copper noise, the thermal noise in the copper. The second is noise that couples in from the body, because the body is conductive and the spontaneous thermal fluctuations in the body couple into the coil through the electric field. We model that as RS, or our sample. And then there's radiation losses, which are typically small in the field strengths that I work at, 7 Tesla and below. So we focus on those first 2 sources of noise, and the SNR is going to scale with the B1 field divided by the square root of the total noise resistance, proportional to this. And image reconstruction from multi-channel coil data is a very interesting and rich topic. Here, I will only briefly touch on the 2 most common ways of reconstructing an image from the multi-channel data. One is to simply do a root sum square coil combination, where we take the multi-channel data, turn it into an array, and multiply it by itself and take the square root. If you want to explicitly incorporate the noise properties of the different elements, you can weight this coil combination by the inverse of the noise covariance matrix, which is related to the noise resistance. And that will weight the noisy channels less in the combined image, which makes sense. If you want to get optimal SNR throughout the field of view, you weight the better channels more and the noisy channels less. So the noise resistance can be computed as the electric field integrated over the volume of interest. If you're looking at noise in a single channel, I and J here would be the same index. You can also get the noise correlation by computing every combination of I and J over the array. So you get a noise matrix, which we'll return to later. Now, how do we know if we're in the so-called body noise dominated regime? Well, if we measure the Q of the coil in free space, we're only going to incorporate losses from the copper and from the components in the coil. So that's RC. If we then measure the Q when we load the coil with the body, we also see that sample noise. And so you can take what's called the Q ratio, which is proportional to the ratio of sample noise to coil noise. And typically you want a high Q ratio because as you load the coil more, you are coupling in more noise from the body, but you're also increasing your B1 minus field inside the body, hence the signal scales as well. So you can't get around the body noise, but you can make the body noise large compared to the copper noise in the coil. That's so-called body noise dominance, which you'll hear about a lot. And you typically want your individual elements to have the Q ratio greater than 2. So the Q ratio is a rough guide for how big to make your loops and how many to use in an array. You can measure the Q at different field strengths. These are the 2 most common field strengths I work at for in vivo MRI, 3 and 7 Tesla. And you see that the Q ratio does go down with the loop diameter, but it's higher at 7 Tesla because you get more electric field coupling into the body, more loading of the coil, all other things being the same. So if you want to stay above that Q ratio of 2 or greater regime, you can look at loop sizes that we would typically use in different channel count head arrays, a 32, a 64, a 96, and a 128. And you see that as you get to this 128 channel, very high density array, you would no longer be body noise dominated at 3 Tesla. So it wouldn't make sense to go to such a high channel count. But at 7 Tesla, you still are. So in fact, one of our most recent projects has been to do 128 channel 7T coil to explore its performance based on this prediction. So to understand the physics of multi-channel receive arrays, you can actually compute what's called the ultimate SNR, which is the best SNR you could get with a certain number of coils on the surface, ignoring copper losses, just looking at the fundamental limits of the signal to the sample noise. And what you see is, as you increase the number of elements on a sphere around a region of interest, you get closer to the optimal SNR of 100%, but at higher field strengths, you don't get as close, especially toward the periphery. So adding more coils helps you a greater amount at higher field strengths, and it helps you especially at the periphery. At the center of the field of view here, you can see that with even 16 channels, you're already getting close to the optimal SNR, but not at the edge. So people have modeled this behavior and looked at how the current patterns created by loop arrays interact or influence the SNR. And what you can see is that if you simulate the ultimate basis set of currents on a spherical surface, which is the best possible for a given field strength and a given geometry, as you add more and more coils to the surface, going from 8 to 64, you can start to better approximate those ideal current patterns. Where you only have a few loops, you can't get close to the ideal patterns. And there's some nice literature about this from Riccardo Lattanzi. Okay, so what happens in practice when we measure coil performance? We see very clearly here comparing volume coil to 8 and 32 channel coil. 1D profiles show gains in SNR, especially at the periphery. You also get a gain at the center here because the helmet was close fitting instead of loose fitting like the volume coil. And we've also compared 32 and 64 channel arrays, showing that you do get a boost in sensitivity, especially at the periphery with the higher channel count. And extending this further, we've been looking at 128 channel array, simulating and measuring performance in the brain. Here you see an extremely high density of channels, as well as the associated low noise amplifiers or preamps and the cables. And we do in fact see gains in the periphery compared to the 32 and 64 channel coils. So that's good news, but we can go even further and do parallel imaging with these coil arrays. And parallel imaging exploits the fact that you have independent coil sensitivity profiles, the magnitude and phase for the different channels in the array. So if you just plot the images you acquire with one coil at a time, you can clearly see that they're quite independent from each other. And so using this to spatially encode, you can essentially fill in missing k-space lines and undersample your k-space data, reconstruct a full field of view image, and go faster, basically acquire less data and exploit your massively parallel array to get a fully sampled image with very minimal aliasing artifacts. And the way you can assess parallel imaging performance is with the noise correlation matrix or covariance matrix, which will be 1 on the diagonals for the correlation. The off-diagonal elements tell you how correlated the noise is from different channels in the array, which is also an indication of how correlated the signals are. So if you have a 32-channel array, you can undersample in this vertical direction by 2, 3, or 4-fold, and you can see how the noise amplification changes as a function of position in the field of view using what's called the G factor. And that will scale your SNR relative to a fully sampled acquisition. And the G factor tells you how well conditioned this image reconstruction inverse problem is. And with more channels, you clearly get a boost in your G factor performance. You can see that here. This is a 96 channel coil at 3T that was able to go all the way to an 8-fold undersampled case. You do see some noise amplification, but it's remarkable. You can still recover an image in 1/8 the acquisition time. Here, I realize it's quite a busy slide, but we're looking at a variety of 1D and 2D undersampling patterns for 32, 64, 128 channel coils. And I would just point out that as you go from 32 to 128, you get a 50% boost in the average retained SNR. So you're really getting a massive performance for a 5-fold undersampled acquisition. And in this case of a 4x4 undersampled in 2 directions, you get 65% boost. So this improved conditioning of the image reconstruction has a real impact. There's another nice trick you can play with these coil arrays, which is called simultaneous multi-slice acquisition, where you actually exploit the fact that the different rows of coils preferentially receive signal from different slices. And in a 2D multi-slice acquisition, you can let the slices alias on top of each other and then tease them apart using your multi-channel coil data. So you can make this perform better if you do what's called blipped CAIPI. Without going into the details, what it does is it uses a phasing code blip to shift those alias copies in one direction in the field of view, which makes them easier to unwrap from one another. And here you can very nicely recover the 3 aliased slices and speed up your acquisition by a factor of 3 potentially. Really nice trick. Okay, so after that sales pitch, let's get down to nuts and bolts, talk about how to characterize received loop performance and tune up coils. So my colleague Lincoln Craven Brightman, who's helping me out today, has made a really nice LT-Spice simulation tool that we've shared and you guys can download from our website, which has a very simplistic model using lumped elements of a tuned loop and plots a few of the most important coil performance metrics, which we'll go through one at a time. But all of the simulations I'll show use this very simplified lumped element model with open source circuit simulation software that you can download on the web. So at this frequency range, you can still get away with lumped elements. If you were up in the gigahertz range, you'd probably have to move to a more distributed model. But the first thing we want to do is tune and match the coil. So what we're actually going to do is simulate 2 probes or a double probe, which are decoupled from each other, but lightly coupled to our resonant loop. Here, we know that the noise and noise sources are modeled as a resistance. L1 is the inductance of the loop, and then we have a few distributed capacitors. To tune it on resonance, we know the reactance vanishes, and you're left with just your resistive part, which depends on the body load, and you need to impedance match the coil to that after you load it on the body. You typically want to match it out to 50 ohms. So if you look at your open circuit resonance with a double probe, it looks like this, and you can see a very nice high key resonance. Now, if you want to match out so that at your port looking in, Zn is 50 ohms, you have to come up with a matching topology. Here, we're using a very simple matching circuit where we use one of the tuning loops as part of the match, add another series capacitor, and then we have to pick those values appropriately. I like to pick the values using the Smith chart. Very briefly, the Smith chart lets you look at impedances and reflection coefficients by plotting them on these circles where either R is fixed and X, the reactance varies, or great circles where X is fixed and the resistance varies. And it has a capacitive and inductive region. And as you add more elements to your circuit, you move around on the Smith chart. You can even have an admittance chart plotted with your impedance chart. Here, the admittance is shown in the gray lines, gray circles. If you stir it for a while, it actually makes sense and becomes a very useful tool because you can then move on either your impedance or your admittance chart in different ways, depending on whether you add a series or parallel capacitor or inductor. You have very simple ways of moving on the Smith chart with those additions to your circuit. And what you want to do is get to the center of the Smith chart, which is normalized to 50 ohms. So that's like the target. You can also move on the Smith chart by adding a length of transmission line, and that just moves you in a circle around the center from wherever you started. If you add a half wavelength of transmission line, you end up back where you started. If you add a quarter wave, it's a useful trick because you can go from being at 0 or short circuit to infinite impedance or an open circuit. Okay, so for our example coil here, we're going to look at these 2 elements. We start out with an impedance point here on the Smith chart. We then look at what happens when we add the correct parallel matching capacitor. That moves us onto this circle, which intersects with 50 ohms in the center. Adding a series capacitor, we move down that circle to the center. Voila, we're impedance matched. So before we've added our matching network, we have this input S11. S11, it's the power coupled back to port 1 when we inject power into port 1. And once we have the appropriate matching topology, we get a nice impedance match, which means power will couple in and out of the coil properly. Okay, but it's not enough to tune a coil because we also need to protect the coil and protect the preamplifier when we have RF transmission. And in my coils, the RF transmit will be separate from the receive array. It'll be a separate volumetric transmit coil. So we don't want to leave this circuit tuned, or it will couple to that body coil during transmit. So you want to break the resonance by creating a little blocking circuit inside your loop. And the way we most typically do that is with what's called an LC trap circuit. It forms a parallel resonant circuit when you turn it on by supplying 100 milliamps to a diode, which acts as an RF switch. The impedance then becomes infinite at that point in your circuit and blocks current. And if you then sniff the resonance of your loop with a double probe, you'll go from seeing a very nice open circuit resonance like this to seeing a spoiled resonance where you get this characteristic M shape. And you're now blocking RF from coupling into your circuit on resonance, which is what we want. Okay, you can tune up your LC traps using a little sniffer probe like this with the rest of the coil disconnected. And when you enable your PIN diode, it's essentially switching just like this from a nice strong resonance to that M shape. That means your PIN diode detuning is working. Okay, but you also want to make sure you're not getting correlated measurements from neighboring coils. So you don't want the signal or the noise in those two channels to be highly correlated. So you don't want those two loops to couple. So those two loops, unfortunately, being nearby, have mutual inductance, and that mutual inductance will cause them to couple. And typically, the way we avoid that problem is by taking the two loops and adjusting the spacing between them until we get what's called critical overlap, where the mutual inductance cancels. That's where the flux through the overlapped part cancels the flux through the rest of the loop. And that works very nicely to make those two coils independent of one another and improves parallel imaging performance. Okay, and so the way it might look in practice, you start with one loop, you add another loop, they couple and you split the resonance. That's not good. You overlap them the appropriate amount and you've got your resonance back. So the way you measure this on the bench, here's two coils that we want to decouple. Look at S21, which is power transfer between those two elements. You go into one element and out the other, make sure they are both tuned and matched to Larmor. That's very important. Otherwise, you won't get an accurate measurement. You want them to be loaded with a realistic sample. And then just make sure that you get, less than minus 12 dB coupling between the two. And then I would consider that well decoupled. Okay, if they're not decoupled, you just adjust this overlap, maybe by pinching the wires to change the flux through the overlap region until you get a acceptable S21. Well, you might ask, what if you're trying to also decouple two elements that you can't overlap because you have a large array and these two red elements don't overlap? How do we make their measurements independent from one another? Well, it turns out there is a trick for doing this, and it's called preamplifier decoupling. Preamplifier decoupling uses a transformation of the preamp input impedance in order to present a low impedance at a spot near the drive point to your coil, using a suitable transformation network in between. And if you can present the right impedance, here a low impedance between this point on L1 and ground, you're now creating a trap between L1 and C2, and that will block current in your loop, which has the same effect as a PIN diode detuning. You may ask, well, if we're going to spoil the resonance of our receiver while the preamp's hooked up, doesn't that ruin the coil? And the tricky thing to grasp is that we've actually converted this from a power or current measurement into a voltage measurement. So we're no longer allowing current to flow in the loops, but we're still going to have a voltage across the drive point. However, loop A and loop B, you will not have current in loop A. Therefore, loop A can't induce current in loop B. Therefore, it can't change the voltage detected in loop B. So it's improving the independence of the voltages measured in the two loops. And the preamplifiers are specially designed to do a voltage mode measurement so that this doesn't compromise the sensitivity. So it's a very nice trick, and it can decouple all of the elements in an array from one another. Well, how do we do it? Here's just another schematic showing that we are coupled between these two elements, but we've presented the appropriate impedance at the drive point to basically block the circuit there. So the way we do it is we look back toward the preamplifier from the drive point of the coil, and we make sure that we've got an appropriate impedance transformation from the input of the preamp to the drive point so that we have a high impedance at the drive point. Now, the preamps are often designed with a low input impedance of, say, 2 ohms. to facilitate presenting a high impedance at the drive point if you transform by a quarter wave transmission line. So here's just an example. We're going to add our transmission line, then a matching capacitor, another capacitor, and this ends up being around magnitude 35 ohm impedance, which is, it's not perfect, but it's much better than having you know, a short circuit or a low impedance at the drive point. So this will tend to block current around at the drive point of the circuit and provide decoupling. So how does this look in our simulation? Again, we start with our open circuit resonance. Then we connect up our preamp with the appropriate impedance transformation, and we get an M shape, just as we did for pin diode detuning, which will tend to spoil the resonance of the circuit, prevent current from flowing, and reduce inter-element coupling. Here's just an overlay of those two plots showing a double probe measuring a coil with and without the preamp present, and showing that you get this nice, in this case, almost 20 dB of blocking between the open circuit and the preamp decoupled states. Okay, in our simulation, you can again see our preamp decoupled curve, and our, this is mislabeled, sorry, that should be pin diode detuning in green. The pin diode detuning is actually a higher Q circuit. It's better at spoiling the resonance of the loop, because you really want to block any transmit power coupling into the coil, because it's a safety issue and it's for protecting your preamp. So that's right in the loop. So you can get a very high impedance at that point. The preamp decoupling is not quite as high a blocking impedance, but you see it still does do quite a lot to help with inter-element coupling. So yeah, so then you might ask, well, we're using the same matching network to both transform our coil impedance to 50 ohms and to transform our preamp input impedance to a high impedance at the coil terminals. How do we do the same thing with this? How do we accomplish both of these tasks using the same elements, doing double duty? And there's a nice paper from Arne Rakowski that shows how to analytically compute component values using one of these four matching network topologies to automatically give you values that should work. Okay, so one final thing you want to measure on your coil is common mode currents. Common mode currents are when the current on the center pin and the shield of the coax go in the same direction instead of the differential mode where they're opposing directions. And common mode currents can be a big problem, especially on the output cable going from your preamp to your scanner or spectrometer. They can cause heating of components such as the cables. If you have common modes, you can also get coupling between channels through the common mode, which is a big problem, and it makes the whole system less stable. You want to eliminate fields outside your cables. You can measure common mode along a cable by coupling in with these ferrites, and you can block the common mode using any number of balins or cable traps. Here, we're actually taking a whole bundle of cables and has a shield on it. We wind that into an inductor, put a capacitor across it, and we make a high impedance LC circuit on the common mode. So it's not going to affect our signal on the inside of these individual cables, but it's going to block the common mode on this braid on the shield. So there's other ways to do this, or floating traps, bazooka balins, lattice balins, and others that you may have heard of. But you want to make sure that you get a nice null at your Larmor frequency using the common mode probes. Okay, so to make all these measurements, you want to create some handcrafted probes, such as double probes, sniffer probes, single probes, and current injection probes. These are really important to have in your lab for building arrays. And you ideally want to have a test rig or a scanner socket simulator. This is where you can plug in your coil just the way you would on the scanner and have a preamp bias supplied to all the preamps, as well as a pin diode bias supplied to all of the pin diodes in the circuits. And even better is if you have switches on your pin diodes, so you can tune them one at a time with all the other elements detuned. So it's worth investing in some test equipment like this. These are the things you want to include when you're building it. So building an array in practice, we usually start with a 3D CAD model that can be 3D printed and conforms to the body. And we try to fit 95% of adult head shapes and sizes inside these. helmets. You want to get as close as possible while still fitting most people's heads. And then you populate your elements, including the wire loops and all the passive components. Then you add your preamp boards, and then you wire it up to the scanner. And one final thing you want to be careful of is the orientation of your preamp in the main B0 field, because some preamps have a Hall effect issues with the FETs inside the preamp. And there will be a preferred orientation for the preamp. So check with your vendor to make sure you get your preamp lined up correctly so it doesn't have compromised gain inside the main field. These are some useful non-magnetic components that you might want to buy for building coils. You can look through this later if you download the talk. And I want to refer you to these really nice tutorial videos from Boris Kyle, available on the ISMRM website. He goes through all the stuff I talked about and more. And he's a virtuoso coil builder who does a really good job explaining all of this stuff. And then here are a book that I find very helpful for understanding coil tuning and basic principles, as well as two papers, including the NMR phased array by Pete Romer, which is sort of the classic paper on receiver arrays, as well as a nice review article also by Boris. So with that, I wanted to switch over and use any remaining time for a quick lab bench coil demo. Can the moderators tell me how much time we realistically have left? I realize we started a bit late, but I also don't want to run the session late. So I'm happy either to skip to questions or to do a really quick bench demo.
You have about, we have a little less than 10 minutes. So if you want to do a demo, that'd be great.
Okay, great. So we'll do a quick demo. And then if we don't have time for Q&A, I'm also very happy to answer any questions by email if folks want to follow up with me. So here we have our coil set up on the bench. Oops, and Lincoln, it looks like it's upside down. Yeah, we just need to rotate this around real quick.
Ooh, sorry about that.
Yep. There we go. So what you'll see is we've got a single test loop set up along with a vector network analyzer, which will show the various S parameters that I discussed in my talk. And what I wanted to show first was what's called the Q ratio, which tells us something about how well loaded the coil is on our phantom. And this is just loaded by a sphere phantom that you can see underneath the loop. Here, by the way, is we have the loop, and we have a drive point board with the matching network and the pin diode detuning elements. And then the red PCB would host the preamplifier, which is shown here. So if we couple in now and look at our loaded coil, you can't quite read this, but we're getting a Q of about 100. And if we now lift it off the sample, we get a Q of about 250. So the Q ratio for this particular element spaced this far from the load is about 2.5, which is above that threshold of 2 that I said we usually aim for. If you don't get good loading, at least at high field, it usually means your coils are too small or they're too far away from the load. Okay, so the next thing we want to show is the open circuit resonance of the loop. And so here we are looking at a nice open circuit resonance, just as we did for the Q ratio measurement. And now we want to show you how we match this into the load by looking in through our preamp daughter board. And so we're going to use a small coupling connector to hook up into our input port to the coil. And we see a nice S11 dip. And as Lincoln lifts this off the sample, you'll see it's not loaded as well because we tuned and matched it for this particular sample. And we're running low on time, so I won't go through the exercise, but we have trimmers that are tunable capacitors on the coil. And if you trimmed those, you would see that the resonance shifts around, and you would see that the the impedance match will also change if we change the matching capacitor. So if you increase the loop capacitance, it'll shift down, and if you decrease it, it'll shift up. So just as the theory predicts. So that's the basics of tuning and matching. I also want to really quickly point out that where Lincoln has his tuning stick on the capacitor, we actually usually put a passive detuning trap across this distributed capacitor by adding another inductor and 2 cross diodes, which are not yet populated on this board. And what that does is those passive diodes will turn on if your active detuning pin diode trap fails. So it's a second way of detuning a coil for safety. And if you don't use a passive detuning trap, then the other alternative is a fuse. A fuse, if it blows, you have to replace it. But on any in vivo coil, you want a backup detuning mechanism in case your pin diode trap breaks, in case a wire snaps or solder joint fails. You don't want to have a safety issue where the receive element is tuned during RF transmit and it's interacting with the transmit RF at high power. Okay, so the next thing we want to show is when we put in our preamp, we want to see preamp decoupling, which I think is kind of the most important of all these metrics for a massively parallel array. And when you make this measurement, make sure you set your VNA power low. You never want to have a lot of power going into your loop because your preamp is now turned on and attached. So you don't want to saturate the preamp or even worse, burn it out. So use like minus 20 dBm on your VNA or less. And now you can couple in and see this nice M shape that where there used to be an open circuit resonance. The M tells us that our preamp input impedance is being transformed to a high impedance at the coil drive point, which is good for decoupling the elements in the array. And there you can see it a little bit better. Alarm frequency is right there in the middle where that little arrow is. And now if Lincoln turns on the pin diode, you'll see that the pin diode detuning will dominate the preamp decoupling, and it gives you much better resonance spoiling, and the trough is deeper and those 2 peaks in the M are further apart. So we widen the frequency range on the VNA, and you can see we get a really, really nice pin diode detuning, which you can tune the pin diode detuning either by tuning the capacitor in the trap or the tunable inductor. And we like to use these really nice Coilcraft inductors, which you can see in yellow. Oops, this one. That is a tunable inductor. It's air core and high Q. And if you want to fine tune your trap, that inductor in our topology is not part of the rest of the coil circuit when the pin diode's off. It's just hanging off, open circuited on one side. So you can independently control that to shift your M and put the null right at the Larmor frequency. So as Lincoln's tuning that inductance, you see a nice shift in the M. And so we use this to fine tune our blocking. So then I think we were going to show one other test, which was to show neighbor coupling, but we may be out of time. So I may open it up to questions while Lincoln's setting that up, so we don't keep people unduly.
Anybody have a question? You can step forward to the mic. They're all just waiting for the next demo.
Oh. Okay. Yeah, the last demo was to take 2 loops and look at S21 and show that they're highly correlated if we have them next to each other, or highly coupled. There's strong inductive coupling, and then bring them to the critical overlap, where the overlap amount is about 1/3 of the loop diameter, and show that the mutual inductance essentially vanishes and you decouple the 2 elements. So so if you get those basics down, my final parting message, I think, is to try your hand at simulating all this stuff first with a simplified circuit topology, even in LT Spice. As humble as those models are, they get us pretty close to what we see on the bench. And then once you're happy with your simulation, go out and build it on the bench. And like I said, I'm delighted to answer any questions people may have after the conference.
Okay, well, let's thank Jason. And thanks Danielle, Isabella, Jason, all our speakers for a fantastic tutorial symposium. They're all waving goodbye to you. I realize there's no camera on the audience here. But thanks again for joining us, and and hopefully next DNC we'll see you in person. We miss
Thank you,
seeing
Joanna.
Thanks, guys.
Thanks for having
Okay.
us.
And with that, the vendor suites are open. We got one